All right, last example for this chapter. These examples are a little longer, okay, but they cover a good amount of stuff, so just bear with me. Okay, suppose the time it takes a 9-year-old to eat a donut is uniformly distributed between 0.5 and 4 minutes. So let's write that as a distribution. Our random variable is uniformly distributed between 0.5 and 4 minutes. All right, again, this is going to be something that shows up. We had it in binomial, although I don't think I included in my new notes. Maybe in the future, I'll add that in, retroactively go and add that in. All right, and we're going to see this in normal distribution as well. So it's important we get used to writing this. Our random variable is, that little squiggle is like saying how it's distributed. The capital letter represents the type of distribution. And then there will be two key pieces of information. For uniform, that's a beginning and end point, or our A and B. Find the probability that a randomly selected 9-year-old child eats a donut in at least 2 minutes. Okay, I can't stress enough that you're going to be asked to write the probability statement mathematically. So for us, that's P of what? All right, the probability a randomly selected 9-year-old eats a donut in at least 2 minutes. So I'm just comparing the random variable to the number 2 here. There was no between. All right, and when we say at least, what kind of inequality is that? Is the random variable x bigger than 2, smaller than 2? Can it equal 2? All right, here when we say at least, 2 is the smallest number, meaning the random variable needs to be bigger than, and if it was in the discrete world, it would really matter that we say greater than or equal to. All right, again, in continuous world, which we are now in and will continue to be in moving forward, it's not as big of a deal to have that correct or equal to inequality because the equal to part has no probability that's added with it. Okay, remember the probability of x equaling 2 is equal to 0. It's impossible to talk about an exact value once you're in the continuous world because there's no area. If I drew my rectangle and I had both ends of the rectangle at 2, there's no area. It's just a sliver there. All right, let's draw our picture. We are going from 0.5 to 4 for our uniform distribution. And we have a height of 1 over 4 minus 0.5, or 1 over 3.5. All right, we got our rectangle going. We need to fill in the exact information for part A now. X being greater than or equal to 2. So I'm going to put 2 on there. I don't know, maybe around there. Doesn't need to be perfect. The values being marked are what we really care about, and we want the random variable to be greater than 2. So we're going to shade to the right. All right, now I go and I find the area of this shaded region, base times height. That's 4 minus 2 times 1 over 3.5, or 2 times 1 over 3.5, or 2 over 3.5. When I put this into my calculator, I get 0.5714. So the probability that a 9-year-old child, selected 9-year-old child, eats a donut in at least 2 minutes is 57.14%. Pretty good odds there, more than 50%. Let's try another one. All right, one that's slightly different. We're going to find the probability that a different 9-year-old child eats a donut in more than 2 minutes, given that the child has already been eating the donut for more than 1.5 minutes. So this is our first given situation. We talked about these. We talked about given conditional probability in chapter 3. All right, the formulas for that work the same way here, but I'm going to show us a different way using our rectangle. that can help us. So notice that every example we've done so far, we start with the basic rectangle that goes for our whole uniform distribution. This is similar to the contingency tables where we always had it out of the total, out of the total. For uniform distribution, we always started with A to B and a height of 1 over B minus A. Given conditional probability is the only time that our starting rectangle will change from this original rectangle, going all the way from A to B. So let me write this mathematically real quick. The probability of a child eating a donut in more than 2 minutes, so X being greater than 2, given, remember our vertical line for given, that the child has already been eating the donut for more than 1.5 minutes. So what this basically means is we're finding the probability it takes a kid more than 2 minutes, given that the timer has already been running for 1.5 minutes. So we've eliminated that whole first 1.5 minutes. We know the children are not going to finish in that amount of time because I'm starting my experiment later. Okay, I'm given this extra information. This piece here will alter the starting rectangle. Instead of going all the way from 0.5 to 4, I know, instead of going from 0.5 to 4, I know that I actually am going to be greater than 1.5. So my rectangle is not going from 0.5 to 4, it's going from 1.5 to 4. This is now my starting rectangle, 100% of my probability, which means that my height is also going to be altered. My height is now not going to be 1 over 3.5. It's going to be 1 over 4 minus 1.5. It's going to be 1 over 2.5. Because again, this has to be 100% or 1.00 as a probability, that whole rectangle. So once you have your given information, here it was that X was guaranteed to be more than 1.5, our rectangle gets altered that way. If your given information had been that X is less than 3, then we would have cut off that upper part. This would be my starting rectangle. If I was told that it was going to be less than 3, then I would cut off that upper minute because I knew it wasn't going to be up there if I was given that the child was going to finish in less than 3 minutes. All right, so here we were given that it would take them more than 1.5 minutes, which is why we cut off that bottom minute. We knew that that was not going to help, and that gave us extra probability. It changed the height to be this upper rectangle. All right, so remember this given piece, all it's going to do is alter the starting rectangle, and now we just fill in our shaded region for what probability we're actually looking at. So now I'm going to put 2 on my scale. I'm going to shade above 2. I want the probability that it's greater than 2. And I'm going to find the area of this shaded region. Base times height. So 4 minus 2 times 1 over 2.5. Or 2 times 1 over 2.5, or 2 over 2.5. And when I put that into my calculator, I get 0.8. So you see that on part A and B, we were looking for both being greater than 2. One was at least 2 minutes. The other was more than 2 minutes, given that they'd already been eating for more than 1.5 minutes. Okay, so with this given piece of information, we were able to narrow down our scope of possibilities, and it increased the overall probability of that event occurring. So normal probabilities, we start with our whole rectangle. Only when we're given an extra piece do we alter our starting rectangle, and that will change the height of the starting rectangle as well. Okay, let's try one more percentile question. Oh, just kidding. We will get to that percentile. Sorry, this is going to be a longer video. My apologies. Let's do one more conditional probability. Find the probability that a 9-year-old child eats a donut in less than 3 minutes. Wow. I did say less than 3 a second ago, but thankfully this isn't the given part. Given that the child has been eating the donut for more than a minute. So the given part is the more than a minute. This will alter the rectangle. So instead of going from 0.5 to 4, like our normal situation would, we are going from 1 to 4. The probability of a child eating a donut in less than 3 minutes, given that the child has been eating the donut for more than 1 minute. This is the given piece that's going to alter my rectangle for more than 1 minute. So I am cutting off here at 1. I know that this part over here does not matter. Okay, it's impossible that they finished in 30 seconds, 45 seconds, 50 seconds. We had to know that they were more than a minute. So this now has to be 100%. So that height has to be 1 over this value minus that value. 1 over 4 minus 1, or 1 over 3. That's my height of this rectangle. All right, now I get to fill in x being less than 3. So I'm going to mark 3, and I'm going to shade to the left of 3. All right, our probability is equal to the base times the height. That's 3 minus 1 times 1 over 3. That's equal to 2 over 3. And that's equal to 0.6 is repeating. So rounding to 4 decimal places, we'll round that 4th one up. Since the 5th one was also a 6, it will round that 4th value up. If this is something you're struggling on, please see me in office hours. All right, this is something that once you get it, it's not so bad, but it does take a little bit of a learning curve. So we want to make sure that we get that under our belt early on, this conditional probability and how it's actually altering this rectangle. All right, last but not least, let's practice one more percentile. And remember that this can also be called the minimum of the upper quartile. So our quartiles, we had our lower quartile was 0 to 25th percentile. So the maximum for the lower quartile would also be the 25th percentile. Okay, and I wrote this in here because I think one of your homework questions calls it that. Okay, if it asks for the minimum of the upper quartile, that's the same thing as the 75th percentile, because of our quarters, we had 25, 50, 75. So that's our lower quartile. And that's the max for the lower quartile. This is our upper quartile. And that's the minimum for the upper quartile. All right, so just kind of give you a little bit of extra there. So 75th percentile, remember our rules for the percentiles. We have our basic rectangle. For us, in this example, it was 0.5 to 4. All right, this is not a given. This is not a conditional probability. So we're going back to our basic rectangle. 1 over 3.5, because 4 minus 0.5 was 3.5. Okay, we're starting here. We're looking for the 75th percentile. So some value K such that this area is equal to 75% or 0.75. They give us the probability for these examples instead of giving us a value that we're shading to the left or to the right of. We have 0.75. That's the area of that rectangle there. So 0.75 is equal to the base times the height. Or 0.75 is equal to k minus 0.5 times 1 over 3.5. Now notice this is different than the last example we looked at. In this case, we actually have something being subtracted from k. So it's going to have an extra step involved, okay? We are still solving for k, so our algebra rules are reversed in operation. All right, here, we want to move the furthest things from k to the other side first. So in this case, that's going to be this 1 over 3.5. The opposite of division, which is what 1 over 3.5 is multiplication. If this is something you struggle with, do a lot of these as practice, okay? Because it's always going to be the same 2 steps. There's nothing going to be out of the ordinary. When you're doing percentiles, it's always going to follow these 2 steps. It's a very specific pattern. So, I mean, I encourage you to really understand what's going on, but also you can get around that by doing the practice enough times, all right? If I multiply both sides by 3.5, that eliminates this division part, and then 3.5 times 0.75 is equal to 2.625. And I still have this k minus 0.5. All right, but notice that I did that first, so I don't have to worry about these parentheses anymore. Those parentheses are now gone. This is all alone on one side. K is almost alone, but right now we have minus 0.5. Well, what's the opposite of subtraction? The opposite of subtraction is addition. So I'm going to add 0.5 to both sides, and that will get k fully alone. K is going to equal 2.625 plus 0.5, which is 3.125. That is my k value. That is my percentile. All right, just to finish off the question, let's summarize what this means in the context of this problem. Again, I will ask you to do this, so make sure you're practicing this. What percentage of our children were eating under that 75? Well, I just gave it away. 75%. Okay, I'm talking about the 75th percentile. So 75% of 9-year-old children and what was I talking about in this problem? I was talking about kids eating a donut in a certain amount of minutes, all right? Not 75% of 9-year-old children eat a donut or finish their donut in 3.125 minutes. There's our units. But again, not 75% eat them at exactly that time. It's that time or less. So you have to have that or less written there. I'm looking for the percentage. I'm looking for the context. I'm looking for the units, and I'm looking for the or less part. Okay, so really just kind of practice getting this format of these summary sentences down as you go through all of these problems.